Okay, so today we're going to look at finding the zeros of polynomial functions. And basically, we already been finding the zero polynomial functions, but what we're going to do here is some techniques that will help us find the zeros of polynomial functions that are harder to work with, that are not nice and pretty factoring ones that we've been doing up to now. So there's a lot of techniques in here that help us get to our answer. And we're going to be pretty much putting together everything we've learned up to this point. So first thing we're going to do is something called the fundamental theorem of algebra. It says that if f of x is a polynomial, and that's what we've been working with in this chapter, of degree n, and of course for it to be a polynomial, n needs to be greater than 0, then f of x has precisely n linear factors. So that tells me whatever the degree of the polynomial, I can write the function as with the same number of linear factors, or factors with x to the 0 power. So this is a quadratic, and so I can rewrite this so it has 2 linear factors. Now this is something we've done in the past pretty easily. This is something that can be factored, so I can just factor this polynomial, and I get x minus 2 times my x minus 2. And so I've rewritten f of x as x minus 2 times x minus 2. Those are the linear factors. Then if I wanted to find the zeros, again, I set each of the linear factors equal to 0 and solve, and I get x is equal to 2 multiplicity of 2. Okay, review of what we've done. But what if I have a polynomial that's a little bit harder to deal with, and it has a lot more terms or bigger numbers, something I can't factor, like it's not a quadratic. And so, for example, let's say I have x to the 4th minus 16. Well, okay, this one can be relatively easily factored. I have a difference of squares, so I can factor this to x squared minus 4 times x squared plus 4. And then the first factor here is a difference of squares, so it can be factored to x minus 2 times x plus 2. Now, I still have a quadratic term here. And so I haven't gone all the way because this is x to the 4th, so it tells me I should be able to write 4 linear terms, but I only have 2 linear terms in one quadratic. So, and x squared minus 4 does not factor. So I got to figure out, okay, what can I do to do this? Well, the key is find the zeros first. So I'm going to take x squared minus 4 and set it equal to 0, and I'm going to solve this equation. And if I can find the zeros, then I can find the linear factors. And so solving this, I copy down, it's x squared plus 4. I wrote minus 4, okay. So x is equal to plus or minus. Now, square root of negative. That's what we just learned in the last section. That gives us our imaginary solutions. So I actually have x equals 2i and x equals negative 2i as zeros of this polynomial. And so solving for 0, I see that my two factors would be x minus 2i and x plus 2i. So I could rewrite my f of x function as the product of 4 linear terms, x minus 2 times x plus 2 times x minus 2i times x plus 2i. And there you go. Fundamental theorem of calculus applies. I should have since there's a degree 4 in this problem, I should have 4 linear factors. I found 4 linear factors. Now, the rational zero test is what we're going to use next. And this is going to help us kind of decrease our possibilities, because right now when I look at a polynomial that might not be easy to factor, the zeros have endless possibilities. It could be any real number in the universe, and so I need ways or techniques that I can limit it down. And that's the first thing that we're going to use is a possible rational zero test. So if you have a polynomial with integer coefficients, so it doesn't work with fractions or decimals, but if you have integers coefficients, you can find a combination of all the possible rational zeros that could fall in this equation by doing a ratio of p divided by q. Now, what does p stand for and what does q stand for? Well, p stands for all the factors of the constant term in your original function, your original polynomial. And q stands for all the factors of the leading coefficient. Now, leading coefficient is the number in front of the term with the highest exponent. So it's the number in front of the x with the highest power. So let's see. Let's try one. We got f of x is equal to 2x cubed plus 3x squared minus 8x plus 3. So to figure out my possible rational zeros, won't give me the actual rational zeros, but it give me all the ones that I could choose from. It'll narrow down my possibilities. I'm going to take the factors of my constant term, which in this case is 3, and I'm going to divide it by my factors of my leading coefficient. And my highest degree is x cubed here, so my leading coefficient will be 2. So I'm going to find the factors of 2. Okay, factors are all numbers that multiply together. All pairs of numbers that multiply together equal 3. So that's just 1 and 3, or -1 and -3. So plus or minus 1 and plus or minus 3. And 2's, all the factors are plus or minus 1 and plus or minus 2. Now that I have this, I'm going to simplify this down. So I'm going to take the 1 in the denominator and divide it to every numerator. Now I'm going to take the 2 in the denominator and divide it to each numerator. So I have limited it down from all the real numbers in the universe to 8 possible numbers. So my zeros will be in these, if they have real zeros for this polynomial, it will be one of these 8, or maybe all 3 of them will be these 8. So that's how you kind of narrow down your possibilities. Okay, so I'm going to take factors of my leading coefficient, which is my constant term, which is 12. We don't worry about the positive 12 or negative 12 because we're doing plus or minus for each of the terms. So we're just taking the number. So the factors of 12, well, I could take 1 times 12, 2 times 6, 3 times 4. So my factors of 12 are plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, and plus or minus 12. And factors of 10 are 1 and 10, and 2 and 5. So I have quite a bit of possibilities. Now I can't leave it like this. I got to list all my possibilities. So dividing all the numerator terms by 1, plus or minus 1, I get plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, and plus or minus 12. Now I'm going to divide all of the numerator terms by 2. But when I take plus or minus 2 divided by 2, that's 1, but I've already wrote 1, so I skip over that. Same thing with the 4. 4 over 2 is 2, which we already have. 6 over 2 is 3, we already have. 12 over 2 is 6, we already have that. So now I'm going to divide every term by the 5. And then all by the 10. 2/10 we already have. Let's see, 1/10 we don't have. 2/10 we already have. That's 1/5. 3/10 no. 4/10 we already have it. 6/10 and 12/10 we already have. So again, I didn't narrow it down too far, but I took it from all real numbers to these possibilities here. And so since we couldn't narrow it down as much as we like, and this happens quite a bit, we need some other tools that will help us narrow down our possibilities so we can actually find our rational zeros. Our next little process in our toolbox of skills to do this is called Descartes' rule of signs. So basically, this is not going to tell us the zeros either, but it's going to tell us how many positive zeros I will have and how many negative zeros I will have. So the number of positive real zeros of f is equal to the number of variations of the sign of f of x, or less than by an even integer. So whatever number I get, subtract 2 until I get to 1 or 0. Okay, and the number of negative real zeros of f is equal to the number of variations of the signs of f of negative x, replacing every x with negative x in the polynomial, or less than by an even integer. So subtract 2 by your answer until you get to 1 or 0. Okay, these are multiples of 2 that we'll be subtracting, and the reason for that is because it could be complex solutions, not real solutions. So here's our function f of x is equal to 3x cubed minus 5x squared plus 6x equals 4. So I'm going to find my possible rational zeros. And so I got plus or minus 1, plus or minus 2, plus or minus 4, and then plus or minus 1, plus or minus 3, and my factors of the leading coefficient. So breaking that up, I've now narrowed it down. All right, so let's see if I can narrow it down any more. So I want to find the number of real positive or positive real zeros. All right, so I'm going to take my original function, f of x, 3x cubed minus 5x squared plus 6x minus 4. And I'm going to look at how I sign. So I went from positive to negative, negative to positive, positive, negative. So there's 3 times I switch signs in that equation. So that means I will have 3 or 1 positive real zeros. So I'm guaranteed to have a real positive real zero. Now to find the number of negative real zeros, I take negative f of x, so I replace every x with negative x. Simplify this down. And look at how many times I switch signs. So I start at negative and I'm always negative. So there was never did I switch signs. So that I know there will be no negative real zeros. So this equation will have 3 positive real zeros, or 1 positive real zeros and 2 complex zeros. So I've now eliminated half of those possible. So I only have to check my positive 1, positive 2, positive 4, 1/3, 2/3, and 4/3. And I'm guaranteed one of those will work, but maybe 3 of them will. So that has helped me narrow it down quite a bit. All right, you try this one, next one. All right, let's see how you did. So possible rational zeros test tells me I need to take the factors of my constant term divided by my factors of my leading coefficient. Okay, dividing each of the numerators by 1 or plus minus 1, we get plus minus 1, plus minus 2, plus minus 4, plus minus 8, and then dividing by 2, 1 we already have, 2 we already have, and 4 we already have. So I've now narrowed it down to these 10 possibilities. So now I'm going to look at my possible number of positive real zeros. So to check number of positive real zeros, I have 3 sign changes. So again, there will be 3 or 1 positive real zeros. Now, just because that happened in this case, it's not going to always look like this. I just happen to choose 2 equations that have the same answer here. It'll vary depending on your equation. Now, to figure out my number of negative real zeros, I'm going to replace every x with negative x in my equation and simplify it down. All right, so what to do if we have some that are not real zeros. And then we look at conjugate pairs. So basically what this is saying is if f is a polynomial of coefficients and if a plus bi is one of your solutions, one of your zeros of the function, then a minus bi is also a zero function. So complex numbers come in pairs when you're looking at solutions of polynomials with real coefficients. So find a 4th degree polynomial that has the real coefficients below. So if it has the zeros 1, 3, and 4i, I know these have to be what x is equal to. But if it has 4 minus I as a 0, I know 4 plus I must also be a 0. Because they always come in conjugate pairs. And like we did in the other section, first thing we're going to do is move everything to the left-hand side of each of these little equations to get it equal to 0. And then these are the factors, the linear factors of this polynomial. So x minus 1 times x minus 3 times x minus 4 plus I times x minus 4 minus I. Now, to make your life easier, what you want to do is multiply the 2 factors or all the factors with I together first. And you'll eliminate the i's. Because remember, complex conjugates, when they multiply together, gives you a real number as a solution. So I'm going to distribute x to everything in the second polynomial. I'm going to distribute the negative 4 to everything in the last linear term. And then I'm going to distribute I to everything in the last linear term. Combining my like terms, notice all my terms with I cancel out except for I squared, but we know I squared is equal to negative 1. So I end up with x squared minus 8x plus 16 plus 1, so that's plus 17. And then multiplying x minus 1 and x minus 3 together, I get x squared minus 4x plus 3 times by this x squared minus 8x plus 17. Now I'm going to multiply these 2 terms together, so it's a lot of multiplying. So I'm distributing the x squared to everything in the second parentheses. And then I'm going to distribute the negative 4 to everything in the second parentheses. And finally distributing the 3 to everything in the second parentheses. Combining my like terms, I end up with x to the 4th minus 12x cubed plus 52x squared minus 92x plus 51. And that is what f of x is equal to. So I found a 4th degree polynomial with these zeros that was given. Okay. All right, let's see if we can put what we've learned so far today. So I want to rewrite f of x as a product of linear terms and list all the zeros. So I'm going to start with finding the zeros first. So before I do that, I'm going to use these tools that I've learned today to kind of limit my choices down, starting with the possible rational zero test. Coefficients, factors of 8 are 1, 2, 4, and 8. And then the factors of 1 are just 1. And so for time, that's going to be plus minus 1, plus minus 2, plus minus 4, plus minus 8. So I now have 8 choices. Then I'm going to look at Descartes' rule of signs to see if I can figure out if I can eliminate like all the negatives or the positives, or I can just figure out which is my most bet to choose first. So checking for positive rational zeros, I'm just going to look at the original equation and see how many times we switch signs. So we only switch signs twice. So that means I will have the number of positive real zeros that this polynomial could have would be either 2 or 0. And the reason why it's 0 is if instead of 2, we have 2 complex conjugates. So we could have complex conjugates. That's the reason why we always subtract that pairs of 2. Now let's look at the possible the number of negative real zeros. So we're going to replace f of x with f of negative x. Replace every x with negative x. Simplify it down. And let's see how many times our sign changes. So I switch here, and that's it. So I only switched once. So that tells me the number of negative real zeros I will have is 1. So I'm guaranteed to have 1 real zero that is negative. So I'm probably going to check the negative terms first. Now I could check all 4 of the negative possibilities that I have, negative 1, negative 2, negative 4, negative 8. And then we're just going to see which one works. Once we find one that works, then we don't have to go any farther. Now, how do I test this? Well, I recall that if I do synthetic division and I get a remainder of 0, that number is a factor or a 0 of my polynomial. So I'm going to do synthetic division. And what I'm looking for is see if I get a remainder of 0 or not. Oh, I picked well my first choice. So that is a remainder of 0. So that tells me automatically that x minus 2 is a 0 of this polynomial. So I found my first 0. Now I started with an x to the 5th, so that means that this polynomial is now x to the 4th, and I'm going to try another one. Now I don't want to waste my time trying some more negatives because I only have one negative solution. So I'm going to try some positive and see if I can find a positive one that works. So trying one, I works. I got lucky. I picked well again. And so I know x equals 1 is a real 0. Now I'm going to try again. Now I could try 2, I could try 4, I could try 8, but I'm going to try 1 again because, again, remember, you can have multiplicity. It just tells you the number of it, doesn't tell you unique answers. So I'm trying the 1 again, and look, oh, it does work. So x equals 1 is a 0. So it just happens to have multiplicities. Now, notice now that I'm down, I started with x to the 5th. I now have this term here is x squared. Once you get to x squared, once you put the x's back into your synthetic division, it's x squared, stop doing synthetic division. Solve it by factoring. If it does not factor, solve the quadratic by any technique that we've learned. Factoring, complete the square, or you can do quadratic formula. And that's going to come the most popular one that we'll be doing later on. Right now, this one just solves pretty easily. So all my zeros of this polynomial is negative 2, 1 with multiplicity of 2, and then plus or minus 2i. And again, I had 5, my degree 5, so I should have 5 linear factors. So to find our linear factors, we set each 0. We say x is equal to each 0 that we have, and then set that, solve for 0, set it equal to 0. And then rewrite f of x as a factor, as numbers multiplied together of all these factors. So that's going to be x plus 2 times x minus 1 times x minus 1 times x minus 2i times x plus 2i. And there we go. It was a degree 5, so I should have 5 linear terms here. 1, 2, 3, 4, 5. Check. All right, let's think of another way. What if I did these in all those tests we've done so far, just limits it down to still quite a few, and I don't have time to go through all of them. Well, there's a way that you can eliminate some other choices, and it's called the upper and lower bound rules or test. So if f of x is a polynomial with real coefficients, and it has a positive leading coefficient, so the first term is a positive number, you can apply this upper and lower bounds. Okay, so you can use synthetic division. And if the number you're dividing outside the synthetic division is greater than 0, positive number, and then the last row when you do synthetic division, so the answer you get in synthetic division, including the remainder, is all positive numbers or all zeros, positive numbers or zeros, because 0 can be considered positive or negative. Then C is considered the upper bound of your real zeros. So that means you will not have a real 0 larger than C. Every 0 will have to be less than or equal to that C. And if C is a negative number, and you do synthetic division. And in the last row, your answer row there, you get alternating signs. So alternating from positive and negative. So you can start positive and negative. Positive, negative, etc. 0, if you get any 0 entries on that last line, they can count as positive or negative, whichever one you need for the pattern. If that happens, then you have C is now a lower bound, and you will not have any zeros smaller than C. All zeros will be equal to or greater than C. So let's put all of this together and find all the real zeros of this polynomial. So I'm going to list all my possible rational zeros. So this is my starting point. It gives me possibilities that can work. So finding all the factors of numbers that multiply together equal 24. I gave myself a little too much room there. Let me move these closer. So I've taken from all the real numbers in the universe down to these 16 possibilities. Because my Q is plus or minus 1, so I don't have to write that. It's going to all simplify to plus or minus 1. So I got 16 possibilities. Now I'm going to get it down even farther. Okay, so I'm going to try Descartes' rule of signs. So I'm going to look at f of x, and I'm going to count how many times the sign changes from positive to negative or from negative to positive. So I have one change here at the very beginning, and then one at the end. So I had 2 changes. So this tells me that the number of positive real zeros will be 2 or 0. Because it could be 2 if they're real number solutions, or it'll be 0 if I have a pair, I have conjugate pair, complex conjugate pair. Now I'm going to replace every x with negative x and simplify this down. I'm going to go ahead and just simplify it in my head. Be careful in doing this in your head. Make sure you don't make any mistakes as you're doing your head. If you need to write down the replacing every x with negative x, do that. All right, let's see how many times it switches signs. So, only once. So I will have exactly 1 negative real zero. So I'm going to start with the negatives because I'm guaranteed that there's going to be 1. There might not be any positives. I might waste my time trying the positive. But before I do this, I'm going to see if I can narrow it down even farther because there's, like I said, there's 16 possibilities or 8 negative numbers to try. I don't want to do synthetic division 8 times if I don't have to. So how do you figure out what to try? What I usually do for starting this upper bound, because it could be any of those zeros that you have listed as your possible rational zeros, I usually start with somewhere in the middle. And that way maybe I can hack off about half of it. So I'm going to start with negative 6 to do a lower bound test. I'm doing my lower bound test. So I'm plugging in the negative here into synthetic negative 6 and doing that into synthetic division. And let's see what we end up with. Okay, so obviously negative 6 is not a 0 because I didn't get a 0 as a remainder. But look what happened. I got positive, negative on that last row. So I'm using my 0 that I'm testing as negative. And so if I do positive, negative, that means that negative 6 is a lower bound. So I will not have any zeros smaller than negative 6. So from our possible rational zero test up here, I can eliminate negative 8, negative 12, and negative 24. So I've got my choices down to slightly smaller. I've eliminated 4 choices with doing only 1 synthetic division. So now let's try see if we can get an upper bound. So upper bound, I want to pick a positive number. And so again, I want to pick something sort of in the middle. So I'll try 6, and I'm going to divide that into my original polynomial. And this time I'm looking for, if I get all positive answers on this bottom row, then it will be a upper bound. But if I get any negatives, it's not. And I'll have to try another 0 possibility up there. Just choose something larger than what I tried. But I did work. Notice all of my last row is positive. And I'm doing my 0 I'm trying, or the number I'm trying, is a positive number. So that tells me 6 is the upper bound for these possible rational zeros. So now I can eliminate all numbers, and obviously 6 is not because I didn't get a remainder of 0. So I can eliminate 6, 8, 12, and 24. So I've now narrowed down my possibilities to these 8 possibles. So I've took away half of my zeros, but doing 2 little synthetic division. All right, now, how do I actually find the zeros? Well, let's put it all together. So from Descartes' rule of signs, I know I will have 1 negative answer. And I have 4 negative numbers to try here. -1, -2, -3, and -4. So let's just try them. You're just going to pick one, and you go into trisynthetic division. If you get a remainder of 0, you're good. So that's kind of what we're looking for here. So I'll start with, let's try -1. We'll do synthetic division here. Now at this point, it's obvious that I'm going to have a remainder, so I can stop. So -1 didn't work, so I'm going to move to my next negative. Let's try -2 and see what we get. Okay, so that gave us a remainder of 0. So I know x equals -2 is a 0 of this polynomial. And it is a -0. And by our discard's rule of sign, we only get one negative. So I won't have any more negatives. And I started with an x cubed, so that means that this is now x squared. So I'm going to put my x's back in. I got x squared minus 7x plus 12. And then I'm going to see if I can solve this quadratic. Now this one does factor. If it did not factor, I would do the quadratic formula. But it factors. And it does factor to x minus 4 and x plus 3. Set each of those equal to 0. And I get x equals 4 and x equals 3. So this is a case where I had 2 positive and 1 negative 0. So my 3 zeros would be -2, 3, and 4. And we found all the zeros of this polynomial. All right, what we've been doing, what we just did in that example is putting it all together. On your quizzes and tests or stuff, sometimes I'll leave it as that question is the last one, put it all, just find all the real zeros, and you have to know to do the steps, or I will lay out the steps like I did here in steps A, B, C, D, and E. So sometimes I'll give you the steps, sometimes I won't. So here I'm giving you the steps, and so we're just going to do f of x is equal to x to the 4th. So we're going to start with finding our possible rational zeros using our possible rational zero test. So I take all the factors of our leading coefficient, our constant term. So all the factors of 48. So now I'm going to multiply together to equal 48. Well, that'd be 1 and 48. And make sure you put the plus or minus every time, because it could be 1 times 48 or -1 times -48. So there are always two possibilities. So 2 times 24, 3 times 16, 4 times 12, and 6 times 8. All right, and then my leading coefficient is 1, so plus or minus 1 is our denominator, so we don't have to worry about that. It just all cancels out to it. So those are our possibilities. I went from all the numbers in the universe to just these few. Let's narrow it down some more. So let's figure out how many, if we're going to have any positive or negative, and how many of we're going to have of each of those by doing Descartes' rule of signs. So we look at our original function to test to figure out our negative ones. All right, so I got one switch and one more, so 2 switches. So that tells me that I will have 2 or 0 positive real zeros for this problem. So I may or may not have some positives. If I do have one, I have another one. I have 2. Okay, replacing every x with -x and simplifying it down. I get this polynomial. Let's see how many times are we switch signs. So we have 1 and 2. So this time I'll have 2 or 0 negative real solutions. All right, so that didn't help us eliminate anything. I couldn't eliminate the negatives or the positives. So let's try our upper and lower bounds. And we're going to try and see if we can find upper and lower bounds. Here I got kind of 2 numbers in the middle, 6 or 8. I could pick whichever one. I'm going to try 6 first, because that way I can eliminate more zeros if it works. But if it doesn't, I would try the 8s. So I'm going to start with -6 and check for my lower bounds. So I do synthetic division with -6. Simplify it down and see what do we get. Now, since this is a negative, I'm doing by a negative number, I'm hoping my terms on the bottom will alternate from positive, negative, positive, negative. So far, so good. Excellent. So this does work. My answers there, my terms on that last row is alternating from positive to negatives. So I know -6 is our lower bound. So I now can eliminate all those zeros that are smaller than -6, which is -8, -12, -16, -24, and -48, as well as a -6 since I didn't get a 0 there. So now I'm going to do my upper bound. I'm going to try 6 again. Now this time, since the number I'm trying is positive number, +6, the upper bound test says that I should get all positives on this bottom row. So far it's good. Yes, I got all positives. So that tells me 6 is an upper bound. So all my zeros have to be in between negative 6 and 6. And since when I did the synthetic division with 6 and negative 6, and I did not get 0 as an answer, I can exclude the 6 and negative 6. So my new list of possible rational zeros have been narrowed down to plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 4. So I got 8 possibilities. So now it's just trial and error. We're just going to do synthetic division until we work it. Now this time, it doesn't matter if you start with positive or negative, because each of them have possibility from discussable sign of 2 positive or 0 positive and 2 negatives or 0 negatives. So I got an equal chance either way, so it doesn't really matter where I start. So I'm just going to pick a number to start with. I'm going to choose 1, because it's the easiest one to work with. And I want to see what kind of remainder I get. So at this point, it's pretty obvious that I'm going to get a remainder, so I can stop, and 1 doesn't work. So I'm going to try 2, my next positive one. And this one worked. I got a remainder of 0. So I found my first 0. So x equals 2 is a 0 of this polynomial. Now, don't go back to the original. Go use this smaller polynomial we have here. And keep trying. I found 1 positive, so I got to have another positive, because it can't be 1. It has to be 2 or 0. So I know there's going to be another positive. So I tried 3. That didn't work. So I'm going to rewrite 1, 1, negative 14, and negative 24. And let's try 4. That's the only one that's left. It should work, because we've tried everything else on the positives. And yes, it did work. We got a remainder of 0. So I know x equals 4 is a 0 of this polynomial. So I found my 2 positive. And I started with an x to the 4th was my original equation. And so with that first synthetic division, I had x cubed. Now I have x squared. So I'm going to put my x's back in. And this one does factor, so I'm going to factor it. And my other zeros would be negative 2 and negative 3. So I'm listing all the zeros of this polynomial, or my solutions to this equation is going to be negative 3, negative 2, 1, and 3. I'm sorry, 2 and 3. 2 and 4. I'll get it straight in a moment. And that's my zeros. The last thing, part E, says rewrite your function as a factor of linear terms. So remember to rewrite your term as a factor of linear terms. All you do is take your answers, your zeros. So our zeros I have here is x equals negative 3, x equals negative 2, x equals 2, and x equals 4. And then solve these equations by getting them equal to 0. Move everything to one side of the equation. And then those are all your factors. So f of x would be equal to x plus 3 times x plus 2 times x minus 2 times x minus 4. Okay, and that's how you put it all together. Now, I know I have another example here, example 9, but I have 2% left, and I didn't bring my charger home, so I'm going to stop here, and you can try this one on your own if you like.